In the upcoming videos, we're going to start with what object-oriented programming is and explore various concepts associated with it, as well as object-oriented design patterns. Just like you need to learn various ways of parking to learn driving and get a license. Nowadays, it's almost essential to have knowledge of object-oriented programming for programming. Programming languages of today, except for a minority like C or assembly, all include object-oriented programming concepts and features, and it has secured its place as a fundamental component of software development. Therefore, whichever modern programming language you choose, in order to learn coding, you have to climb this mountain called object-oriented programming from the start. However, for those learning programming for the first time, object-oriented programming can be an unfamiliar and difficult concept. In this video, we'll explore what object-oriented and its key components are, solely through analogy, without using any code. Those of you who are learning to code for the first time will grasp what object-oriented programming is and why it is used in programming. For those who have already learned about object-oriented programming, and for those who are going to study OODP, through the explanation in this video, it will be a time to look again, or perhaps from a new perspective, at the important components of object-oriented programming. One thing to remember is that object-oriented is a complex concept that cannot be metaphorically compared to anything in reality. Therefore, I would like to mention that what you will see in this video is just one of the many aspects of object-oriented programming. Let's think of software development as building a medieval castle. The developer is a lord who must write his instructions in documents to construct a castle. These documents of instructions are the programming codes, and the laborers to be mobilized for the construction are the resources of the computer. The programming code includes instructions on what to order the laborers to do. The most primitive method is to list each command to the laborers. Go to the forest and cut down trees. Trim the cut trees into timber. Make a beam with those timbers. Mix cement and sand. Pour water and mix it to make mortar. Stack stones in this space using the mortar. Just like this, we're giving each and every instruction one by one. These instructions will continue endlessly, and similar content will be repeated countless times. A code written in this way is very verbose and has a lot of redundancy, which is inefficient. It is also difficult to analyze and modify this afterwards. How can we improve this? First, we can group certain units of tasks together. The first three instructions can be bundled into make wooden component. You can bundle the next three instructions into lay stone. In programming, a unit that groups such repeatable tasks is called a function. Its meaning is different from the function in mathematics or functional programming, but they have a common point in that they include one or more processes. This way, the functions we've created can be reused as much as needed to write more succinct and efficient code. Now developers can command their laborers, alright, from now on, make wood component, this time, lay stone, and so on. This function is a feature available not only in object-oriented languages, but also in non-object-oriented languages like C. Up until now, we've been dealing with procedural programming. This means it's not object-oriented programming. We have improved the reusability and efficiency of our code with functions. But as the size of the software grows, this alone will not be enough to manage code complexity. This is where the concepts of object-oriented programming come into play. We are going to define roles. These roles are called classes in object-oriented programming. In the process of building a castle, such classes as the carpenter, mason, blacksmith, and engineer are mobilized. Basically, we're defining jobs. In this tutorial, we're going to call them classes and roles. Each class has its own data and functions defined for the role. This data is referred to as attributes, properties, or fields. In this video, we will call it attributes. These attributes are the state each of these laborers responsible for this role possesses. And the functions in the class are called methods. These are the actions these laborers can perform. For example, in this carpenter role, tools used by the carpenter and the blacksmith who makes those tools are attributes. And the work the carpenter does, namely make wooden component, is defined as a method. The key here is this method. Each role assigned laborer takes on the responsibility for this action. Attributes are just the data needed to perform this responsibility. Masons have the responsibility of stacking stones, blacksmiths have the responsibility of making tools, engineers have the responsibility of engineering in the form of a method called function. In this way, in object-oriented programming, before starting the construction of a castle, these roles and their respective responsibilities are first designed and defined. Then you tell the laborers, you are carpenter 1, you are carpenter 2, you are the mason, you all are blacksmiths. Like this, after assigning everyone their roles, you make them work. Imagine you're overseeing manual laborers to build a castle. Rather than just ordering them around as I initially showed, you will easily understand that this method of defining roles and assigning them to laborers is a much more systematic and manageable way. The code of object-oriented programming is usually modularized like this, separated by classes. If there's a need to modify the program, you can just find and modify the corresponding class. It also becomes possible to reuse one class in multiple programs.
So, you're saying we can use the carpenter class later in programs that build houses or bridges?
Yes, that's right. We call the laborers assigned to this role that we call a class, an instance, or an object. These objects are chunks of data that have data about the attributes and methods they are assigned according to their role. Because these data are stored in an object, people often misunderstand objects as pockets for putting data. But, as I mentioned earlier, what's important is this method, that is, responsibility. An object is a result of assigning a class or a role to certain memory resources, making it an entity with responsibility. If you haven't learned programming yet, you can stop watching the video here. Through this analogy, you should be able to grasp roughly how object-oriented programming makes a computer work and why it is a method that can make software more stable and efficient. From now on, this is for those of you who are learning object-oriented programming or a programming language that supports it, and for those who will watch the videos about object-oriented design patterns. You will be able to understand the various concepts of object-oriented programming, which were challenging to grasp, more easily. Even if you don't understand what the explanation is trying to convey, please keep watching without feeling burdened. As you look at the code in the following videos, you'll easily understand what it meant. We're going to cover features common in most, but not all, object-oriented programming languages. First, let's learn about encapsulation. These classes usually do not work alone. They perform complex tasks through cooperation with other classes. For example, carpenter objects have a designated blacksmith object as an attribute in this way. They call the methods of the blacksmith object to order the tools they each use. The important thing here is that the carpenter object doesn't concern or interfere with how the blacksmith object fulfills this responsibility of forge tool. You see these plus and minus signs in front of the properties and methods. These items marked with a minus sign are private, which means they're hidden from the outside. So, objects of other classes cannot read or modify this data. This is called encapsulation. No one should interfere with what temperature of fire the blacksmith uses and which anvil he uses. The carpenter simply orders the necessary tools from the blacksmith, and the blacksmith makes and hands them over in his own way. In this way, by making sure each class is only concerned with the responsibility it's undertaken, you can reduce the complexity of the code and ensure flexibility. Typically, each class only exposes certain methods to the outside, using them as a communication interface with other classes. When writing the code for the carpenter class, developers do not need to consider how the blacksmith class is implemented. They only have to call this forge tool method, which the blacksmith has made public. And regardless of how the mechanism of the blacksmith class running forge tool changes later, it doesn't affect any other class's object calling it at all. External factors only get the output of the task through this public method. Think about how tangled and complicated the code can become when you allow classes to interfere in each other's affairs. You might guess why we encapsulate once you envisage it. Next, let's get to know about inheritance. As tasks become complex and voluminous, the types of roles required also increase. For example, in addition to creating wooden parts, like ordinary carpenters, there could be a construction carpenter capable of using them to construct wooden structures. Similarly, a stone sculptor who can carve stones in addition to the work that an ordinary mason can do, and a bricklayer who stacks bricks instead of stone, these roles can be defined. Then, shall we define them as separate classes, just like we defined the carpenter and the mason? We could do that, but there are two disadvantages. The first is that the code becomes verbose because there are overlapping parts. The construction carpenter class is a class that adds its own methods to the attributes and methods of the existing carpenter class. Hence, there is such duplicated code. It would be inefficient if we have to write these one by one every time we create a derived class. and if there are changes in the common features later, we would have to apply these one by one as well. The second is that no correlation is created among these classes with a common denominator. There are classes that share attributes and methods, but these commonalities cannot be reflected at all in programming. Here, the concept of inheritance in object-oriented programming can be very useful. A class can pass over attributes and methods to another class. When we set the construction carpenter class to extend from the carpenter class, the child class, construction carpenter, inherits the attributes and methods of the parent class, carpenter. The developer then sets this relationship and writes any additional attributes or methods that the construction carpenter class will have. This can significantly reduce the amount of code. Similarly, the mason class can have the stone sculptor and bricklayer classes derived as child classes. The stone sculptor class also has its own additional method, in addition to the attributes and methods inherited from the mason class. On the other hand, the bricklayer on the right inherits its parent's methods in a different way. The bricklayer doesn't follow the laystone method the way the parent class handed down. When an object from the mason class executes the laystone method, it simply stacks stones. However, as you can tell from the class name, when the laystone method is executed in bricklayer object, it stacks bricks. So, child classes are created to execute specific methods in a different way. Overriding the parent's method in the child's way like this is called overriding. Inheritance is not only for creating a class with added properties or methods, but also for creating a class that modifies the way specific methods operate. Of course, you can do both. The benefits of inheritance aren't just about reducing code volume through duplicate removal. It's also about being able to group different classes into one category. Construction carpenter is a type of carpenter, and a stone sculptor and a bricklayer are types of mason. This means that a construction carpenter can fit into a place where a carpenter can, and a stone sculptor, bricklayer, can fit in a place where a mason can. For example, arrays or lists that can contain mason objects can also hold objects of stone sculptor and bricklayer. In other words, a parent class can also serve as a category that groups child classes together. And this category can act as a standard that determines which classes can be used in specific positions. There are classes that solely aim to become a category. This engineer class is an abstract class. Abstract classes cannot create instances or objects by themselves. Just like there are no animals that people only call mammal or reptile, we do not assign laborers just an abstract role called engineer. It should be more specific. This class has a method called engineer, but it is only defined by its name and does not specify what it does. Hydraulic engineer and defense engineer classes are child classes of this engineer abstract class. Workers can be assigned roles as objects of these more specific child classes. They can become hydraulic engineers or defense engineers, but they cannot be just engineers. And the specification of what this engineer method does is determined in the child classes. A hydraulic engineer builds waterway facilities, and a defense engineer makes defense weapons. The role of the abstract class engineer is to act as a category that binds its children together. As I mentioned above, a hydraulic engineer or a defense engineer could fit into a position defined for engineer. Within a particular part of the program, when you write a code that instructs engineer to engineer, if you appoint a hydraulic engineer in the engineer's position, drainage will be built. And if you assign a defense engineer, defense facilities will be constructed. It's possible because the engineer's child classes must inherit and have a method called engineer. As such, another way to categorize different classes and assign the same responsibility is through an interface. In languages like Swift, it's called protocol, and there are languages like Python or Ruby that do not have this. Also remember that Go and TypeScript's interfaces are different from those in other languages. In my object-oriented videos, I will explain the interface in the way that is most commonly used, like in Java. An interface allows for different classes belonging to completely different parents to be grouped into one category. If inheritance is like receiving a family name from an ancestor, an interface is like a degree or a certificate. It can be granted regardless of lineage. Bats, flying fish, and pigeons, while each belonging to different classes like mammals, fish, and birds, all have the ability to fly. Therefore, they all implement the flying animals interface. The wagon driver interface is a certification that permits to transport materials using a wagon. You cannot create objects from the interface itself. It's like saying there's no job called wagon driver. All carpenters, bricklayers, and defense engineer need to transport materials with a wagon as part of their job. So, I will apply the wagon driver interface to these classes. It will be designated as a mandatory qualification for these jobs. Now, these 4 classes must implement this transport materials function in their own ways. For example, in the case of this construction carpenter, it acquires the attributes and methods inherited from the carpenter and also its own methods, along with the methods from the wagon driver interface. Also, they all come under a category called wagon driver. They can be elements in data structures made exclusively for wagon drivers, or they can be parameters in functions that take wagon drivers. In a situation where wagon drivers need to transport materials, any of these can be utilized, regardless of what type of object they are. And depending on what object is mobilized, how the transport materials is done will also vary. It's because, like the methods of an abstract class, each class that applies it implements it in its own way. In this video, we looked at various elements of object-oriented using the metaphor of castle construction. While listening to the explanation, some of you may have had various insights, and some of you may still not quite get what all this is about. Just remember the rough content for now, and as you watch the following object-oriented videos, you will be able to easily understand what the metaphors in this video are talking about. From now on, we'll explore object-oriented programming more deeply with actual programming code. I'll meet you in the next video on the topic of the solid principles.